Hello students. Let us begin where we ended in the previous lecture. So, it's been a lot of days. It was vacation and I was quite busy, so I didn't upload lectures in between them. So, let us start today and continue. So, what did we learn in the previous class? We learned about polarization. We learn about polarization. This is what we learn about. So let me check if it is visible or not. Yes, it is visible. So what is the definition of polarization as we have learned? So it is the electric dipole. So we learned about the concept of polarization. Now we are learning about the polarization vector, that is P, capital P. Okay, capital P, and you mark an arrow to represent it as a vector. So it is the dipole moment. It is the dipole moment per unit volume of the material. Okay, of the material kept inside an electric field. Kept inside an electric field. So you have a material and you keep it inside an electric field, and when you keep it inside an electric field, you are going to observe the phenomenon of polarization, and this phenomenon can be quantized by a vector known as polarization vector. Okay, so the definition of polarization vector is that it is defined as the electric dipole moment per unit volume of that material when it is kept inside an electric field. Okay. So what is it? Capital P is equal to NP. Okay, small p, this is small p, this is n. Okay, so n is what and small p is what? Small p is the electric dipole moment of those molecules present inside that material, and n is the number density. Okay, or you can say the number of molecules in unit cube of that material. Okay, so this can, you can write this thing, n equal to number density or the number of molecules present per centimeter cube of that material, and p, the small p. Okay, this is a small p, right, like this. It is the electric dipole moment of a molecule. Electric dipole moment of that molecule, of a molecule. Okay, that molecule is present inside that material. So if you are asked what is the polarization vector or define polarization vector, you can write like this. It is the electric dipole moment per unit volume of the material kept inside an electric field. So if it asks you, then what is its significance, or why do we need polarization vector? So you can write it quantifies the amount of polarization. Okay, it quantifies the amount of polarization of a material. So now we have written polarization vector, and from its definition, let us write that P is equal to that electric dipole moment of that material divided by its volume. So you can write P by volume. Okay, you can write like this. And what is P? It is the electric dipole moment. So Qi or Q into D. Q into D, as you know that electric dipole moment is the ether of the charge times the distance between the charge. As you should remember that electric dipole moments arises due to the concept of dipole, where a dipole is a system of a positive and a negative charge kept very close to each other, and those charges should be equal in magnitude but different in their nature. So there is a positive charge and there is a negative charge, and they are separated by a distance d. So the electric dipole moment associated with this dipole is P equal to Q into D, where Q is the charge. Okay, Q is the charge or any of this charge. So you can write like this. So it is P is equal to electric dipole moment into it or divided by its volume. So now from this point you can be asked about the unit of polarization vector or the dimensions of polarization vector. So the dimensions of polarization vectors are an important thing at this moment because it can be asked, and I think I have faced this question that write the dimensions of polarization vector. So you need not to worry about this thing because you can derive it from this thing, from this formula, and you have to remember that formula. Okay, so what is this? This is electric dipole moment per unit volume. So let us write its dimensions. So what are its dimensions? So let us first write its units, then we'll come to its dimension. So in SI, what should be the unit? It is Q is coulomb, that is C, then multiplied by distance. Distance is measured in meter. You can write meter divided by what is volume, or in SI unit, what is the unit of volume? It is meter cubed. Okay, it is a meter cube. So you can write it is coulomb per meter squared. What is the SI unit of polarization vector P? It is coulomb per meter squared. So you can actually derive its unit and as well as its dimensions. We are coming to dimensions a little bit later, but first of all, the SI unit for the polarization vector is coulomb per meter squared. So let us now derive its dimensional formula. So what should be the dimensional formula? Dimensions, write like this, the dimensions. So what should be the dimensional formula? So you can actually see from the right side, it is Q. Q is AT. Okay, current into time into D. What is D? It is L. Length. What is volume? It is L cubed. Okay. These are the separate dimensions. The dimensions of charge is AD or A1T1. The dimensions of D or length is L. The dimensions of volume is L cubed. So now from this point of view, you can actually write A1 T1 L to the power minus 2. Here we have 1. This 3 goes to the numerator, or it becomes 1 minus 3, that will give you minus 2. So in order to just write like this, you need to write like L to the power minus 2, T to the power 1, A to the power. These are the dimensions of polarization vector. Answer, this is your answer. So you can see that it is quite easy to derive the dimensions of polarization vector. This is the answer. So the unit is unit of P, coulomb per meter square. Dimensions of P is L to the power minus 2, T to the power 1, and A to the power 1. Okay, so what are these things? L is the length, T is time, A stands for current. Okay, so I think we have done polarization vector, the basic thing for which we started. So let us now continue to another concept, but before this we need to see something more. So I hope that you have written all of these things. So from this point I shall continue. So let me just rub these things off. We do not need these things now. So P is equal to QD by volume. So as we know, if it is a given specimen, so what is its volume? Let us just consider that it is a uniform shape. So if it is a right circular cylinder, if this is the length d and this is the cross section A, then volume will be given by, or small a or capital A, you can write anything, it can be given by A into D. The volume becomes A into D, or area multiplied its height or length, anything else. So we have considered that this D and this D matches. So what should be P? P is equal to Q upon A. Q upon A, and these D's get cancelled out. These get cancelled out. So P can be the electric dipole moment per unit volume, or the charge induced per unit surface area. So as you know that it resembles something like that of a density. What is this density? This is density is the charge per unit surface area. So it is, since this charge is induced, let us write Qi. You can also write it here, no need for that now. We shall continue to write Qi from this point. Okay, so P is equal to Qi upon A. Now for Qi divided by A, it is equal to sigma I. It is equal to sigma I. Okay, this is, as you should remember, you should be remembering that we learnt about three charge density. One is linear, the other is surface, and the other is volume charge density. The linear charge density was denoted by lambda. The surface charge density was denoted by sigma, and the volume charge density was denoted by gamma. In this case also, this is area, this is charge, and charge per unit area gives you the surface charge density. Okay, so this is an important thing, we are going to need it later. So if you have noted all these things, I think I should rub all these things off and then continue. So if you haven't written all of these things, you can take a good screenshot from this point. So let me rub these things off. So as we have written, P is equal to sigma I. Okay, this is your equation. This is our one equation. You need to just remember this. We are going to need this equation a bit later. But before that, what we have observed, the polarization vector. The polarization vector depends upon the intensity of electric field. Okay, when a material is placed inside, this is a material, there is an electric field between these plates. So when you increase that electric field intensity, you will be noticing that more and more charge come to this surface. More and more charge come to the surface. That means when we increase the outer electric field, the inner electric field also increases due to the increase in polarization of that material. So that material, the polarization of that material increases, and due to this, we can write that the polarization vector of that material actually depends upon the electric field in which it is kept. So how does it depend? We can observe that, or it has been observed that the polarization increases as the electric field intensity increases. That means P is directly proportional to E. P is directly proportional to E. Okay. So we need to set up an equation that gives us the direct relationship between P and E. Okay. So what is that equation? So it has been observed that P, the dimensions of P. So you can write like this: the dimensions of P, dimensions of P, as we have derived those things earlier, matches the dimensions of the quantity, just follow me, quantity epsilon naught e. Okay, the dimensions of p are the same as the dimensions of epsilon naught e, not only e, epsilon naught e. Okay, so we can write p is equal to some constant multiplied epsilon naught e. Okay, so what is that constant? In this case it is chi. This thing is called chi epsilon naught. So what is chi actually? Okay, so we need to introduce a proportionality factor, and in this case the proportionality factor is chi. So from these things, what is the thing chi? Chi is equal to susceptibility of that metal. Susceptibility of that material. Whatever be that material kept inside an electric field, it has a property known as susceptibility. So chi is the susceptibility of that material. So from this equation you can write chi is equal to P divided by epsilon naught E. This is the equation of chi, and from this point you can actually define chi. So what is chi, or what does it signifies? It signifies how easily a material can be polarized. It signifies how easily a material can be polarized. If that material is not polarized easily, then chi for that material is very small. Okay, or if it is large, that means you can see here, if we increase E, how is this thing going to happen? If we increase E, then P is also going to increase. If both things increase, so we can see that P increase, or for E, for a small E change, so we can see if P increases to a very large amount, we can actually say that chi is very large for that material. Now for that amount of electric field, if P does not increase, or the polarization vector does not increase to that extent, we can actually say that this ratio is small, and that ratio is equal to the susceptibility of that material, and it due to it is quite small, so it cannot be polarized so much easily. So what does chi, or susceptibility of that material, signifies? It signifies that how easily that material can be polarized. Okay, how easily that material can be polarized. So this is the value of chi. It is a constant quantity. Okay, it is a number. Why it is a number, or it is a dimensionless quantity? So you can write that chi is a dimensionless quantity. Dimensionless quantity, a constant quantity only. Okay, a constant quantity, a constant. Okay, for different material chi is different. Okay, and it is only a number. So we have, so at this point of time I will try to jump to another concept. This is so much you have to need. So let us just jump to the other concept. We are going to derive an important relation. So that relation is quite important. It is a very important relation. Okay, it is an important relation. So what is that relation? We'll try to. This is important thing. We note it at this point. So let us just note it at this point. Pi, or P, is equal to sigma I. Just note it. We are going to need it later. Okay. So relation between relationship between susceptibility susceptibility and relative permeability. Relative permeability. Okay, so it is generally a relation between chi and epsilon r. Okay, we are going to find a relationship between chi and epsilon r. Okay, so what is that? So first of all, we need to consider an electric field. This is an electric field. There is nothing inside that those plates. It is a parallel plate thing. There is nothing inside this thing. Okay. So if we know that the electric field, so let me draw a better thing here. So this is a plate system. The charge density is sigma. It is plus sigma, it is minus sigma. And as you actually remember, we have calculated, so we have calculated if sigma is given or the surface charge density for those plates is given to you, then you can actually calculate the amount of the value of electric field inside those plates. What is the value of electric field? Let that electric field be E0, okay, or E naught, since there is nothing kept inside those plates. So E naught equal to sigma by epsilon naught. Okay, sigma by epsilon naught. So you can actually write sigma naught. So no need to write it sigma naught. Okay. Now, so let me just start writing. Let us consider a parallel plate system. Plate system with vacuum inside it. Having vacuum inside. Okay. Sigma equal to surface charge density of those plates. Surface charge density. So if it is vacuum, then electric field E naught equal to sigma by epsilon naught. Okay, this is this thing. Now you need to introduce a plate. So draw the electric fields like this. Now we are going to introduce a material inside this. This is a sigma or the positive charge. This is the negative charge. And since electric field is present, you can actually see that polarization is occurring. Charge are getting induced. The right side becomes positively charged. The left side becomes negatively charged. So an electric field, the electric field E naught is to the right direction, and the electric field induced EI is to the left direction. Okay, now we place a dielectric inside those plates. We place a dielectric inside those plates such that due to polarization, EI equal to electric field inside that dielectric. Electric field inside dielectric. Okay. This is EI is the electric field inside dielectric. Now, if we are going to find out the net electric field, since E0 is greater than EI in every case, not in every case, but in general case, we are considering E0 is greater than EI. Okay. So the net electric field is E. E is equal to E0 minus EI. Okay. We are going to consider this thing. So I am not describing that the left side of the material is negatively charged and the right side of the material is positively charged. So I leave those things to you. I think that you are smart enough to be knowing those things as we have done these things earlier. Okay, so E is equal to E0 over. So now, E, if EI equal rho, stop. I haven't written. So if it is negatively charged, it is positively charged, then it should have a surface charge density. That surface charge density be sigma I by epsilon. Okay, this is epsilon. This is epsilon since this material is different. Okay, I hope this portion is visible to you because the light is being focused at this point very much. So the induced electric field EI is sigma I by epsilon naught. Now you can actually see the net electric field E is equal to E0 minus EI. Okay. So now put these things as we have known, sigma by epsilon naught minus sigma I by epsilon naught. Okay. And at this point, if it is E, at this point you can see that you can put P in place of sigma I. Okay, you can put P in place of sigma I. This is our equation 1, and at this point we took the reference of this thing. Okay, we took the reference of this thing and placed P at this point. Okay, now we divide the whole equation to equation 2 by E0. You divide equation 2 by E0. So at the LHS it becomes E by E0. At the RHS, sigma by epsilon 0 E minus P by epsilon 0 E 0. Okay. Now at this point we replace P, as we remember, as P is equal to chi epsilon 0 E. Okay. So now chi epsilon 0 E. So now this ratio is equal to the relative permeability. As you know that this ratio is equal to relative permeability. And we just place, if it is, let it be a vector. So we need to place now P equal to chi epsilon naught E in its place in that equation. So after replacing P by this, so we can replace just these things by these things. So epsilon R equal to, this is epsilon R, you can actually write it here, epsilon R equal to E by E0. You need not replace these things, okay, you need not replace this thing, let it be E naught. So divided E naught minus P chi epsilon naught E naught by epsilon naught E naught. So at this point you can actually see epsilon R is 1 minus these things get cancelled out. I think some mistake is remaining. No, no, no. At this point, I can see that there is some mistake happening. Yes, I can sense the mistake. So, what is that mistake? R is equal to epsilon 0 by e. Okay, epsilon r is equal to e 0 by e. So, at this point, we have done the mistake. So, what is that mistake? We need to divide the whole thing by e. We need to divide the whole thing by e. Okay. So, from this point, we need to the mistake. We need to find out the mistake. So, E is equal to E naught minus E I. So E divided by E, we get E by E, E0 by E minus EI. What is EI? Sigma I by epsilon naught divided by E. Okay. Now E by E gives you 1. E0 by E gives you epsilon R minus what is sigma I? Sigma I is Pi. P by epsilon naught E. So you can write a P is equal to, at this point, chi epsilon naught E vector and epsilon naught E vector. You can leave these vectors for this moment. So 1 is equal to epsilon R. See, these things cancel out. Epsilon E in the numerator and as well as in the denominator, they get cancelled out. So you can write epsilon r is equal to 1 plus chi. This is your required equation. Okay. So what is the relationship between susceptibility and epsilon r or relative permeability? It is epsilon r is equal to 1 plus chi, the required relation. Okay, it is the required relation. At this point, we committed the mistake. Okay, we had to divide it by E so that these things also get cancelled out. So I did a blunder. I divided the whole equation by E0, which is wrong. So at this point, we divided it by E and that get cancelled out. All of the things cancel out and give out the real relation. That is epsilon r is equal to 1 plus chi. Okay. So at this point, you have understood so many relations that are very important to this chapter, and the later chapters when you shall be reading about magnetism, you shall be reading all of these things, not all of these things, some important thing like susceptibility in the later chapters of magnetism. So at this point I am stopping the lecture, and in the next class we shall be going into the real topic, that is the topic of capacitance. So up until then, take care. If you have any problem regarding the concept, you can actually drop a mail in the given description box. I have given all of my contact details in the description box, and like our videos, subscribe to our channel and share it among your friends. Up until then, take care. See you. Thank you.